So if I wrote something like, I wanted to find the integral of, let me make this cosine, make this x cosine of 2 minus x squared dx. So the whole idea behind a u-substitution, and in general with our methods of integration, if I look at this problem and no one told me how to find the antiderivative, the first thing that I want to be looking for is, does the derivative of one part equal the other part? And if the answer to that question is yes, or almost, then there's probably a u-substitution involved. And the way I think about a u-substitution is that I'm going to build a vocabulary list and translate my problem based on that vocabulary list. This is a little bit like if I were studying a new language and I were trying to learn Portuguese. Then if I was sitting in a class and the teacher asked me a question in Portuguese, until I'm really comfortable with the language, then what I'm probably going to do is think and translate those words into English, decide what my answer is in English, and then respond back to the teacher in Portuguese. So I'm kind of going to do the same thing here with the math. So I'm going to take this problem, which currently is written in the language of X, and translate it to be in the language of U. So when I look at this, I'm going, well, that's really ugly, but this part inside of the cosine, if I take the derivative of 2 minus x squared, I almost get an x back. So I'm going to start building my vocabulary list. And so if I start building that vocabulary list, and I let u be equal to 2 minus x squared, then I'm going to take that derivative. And we could write this as du over dx is equal to negative 2x. But one of the things that we did in 17a, we talked about differentials. And so we actually want to write this as a differential, meaning I'm going to multiply both sides by dx right now, which is going to leave me with the dx over here with the negative 2. Now, when I look at this, I'm trying to translate what's in my original question. And I don't have a negative 2x dx in my original question, but I do have an x and a dx. So I'm going to build my vocabulary list to match what I had in the question. So I'm going to divide both sides by negative 2 so that I have negative 1/2 du is equal to x dx, because that's something that I had in the original question. The other piece that's coming from my vocabulary list is that u is 2 minus x squared, and that's going to show up right there. So I'm going to translate this problem into the language of u, so that x dx is going to turn into negative 1/2 du. And then cosine of 2 minus x squared becomes cosine of u. And if we want, we can take that constant and pull it out in front, just like we pulled constants out in front of our summations. So I'd have negative 1/2 cosine of u du. Now we're going to apply that fundamental theorem of calculus that says, or rather not the fundamental theorem of calculus yet, but now I'm going to say that this notation of this integral symbol and that du mean find the antiderivative of whatever's in the middle. So cosine of u, whose derivative is that? That's going to be sine. So this becomes negative 1/2 sine of u plus a constant. Now, if I'm finding, oh, and just for consistency, I'm going to, no, we're good, sorry. If I'm finding the indefinite integral, and we would call this indefinite because there are not bounds on that integral, if I'm finding the indefinite integral, I'll come back to the question that's on the screen in a second. If I'm finding the indefinite integral, then I now need to translate my answer back to be in terms of x's, because that's how the original question was asked. So this would become -1/2 sine of 2 minus x squared plus c. That would be my answer to the indefinite integral. I go back up to the original problem and pretend that I had actually given us bounds and that we were finding the definite integral from 0 to 3. So one of the things, the extra thing that we have to do in terms of our vocabulary list here, when we have a definite integral, we also need to adjust the bounds to go with our new variable that we're working with in the problem. So that 0 and that 3, those really represent what's happening with the variable that's on the dx. Because remember, this represents an area, and if that dx is the width, then that means that these two go with x values at the bounds. So this is x equals 0 to x equals 3. So when we make our translation into something with u's, we also need to translate those bounds of x equals 0 and x equals 3 into new bounds with respect to u. One of the things to be careful about is normally we expect the number at the bottom to be less than the number at the top. Like if we were setting up for area, we're going from the left to the right. But when we do this translation into the bounds for u, we have to keep them in the same order that they started in, which means in this case, x equals 0 was at the bottom. And when we plugged in 0 for u, we got 2. So that's what belongs at the bottom of our integral. X equals 3 was at the top. So when we plugged in 3 for x, we ended up with -7. So that, whew, my 7 got a little bit big there. That ends up at the top. And I do see the question, and I'm going to come back to it. So again, this is going to look like 2 to -7. So after we've found the antiderivative, now I'm going to plug in the 2 and the -7. So my final answer here, even though it's not pretty because I don't know what sine of -7 is, and I don't know what sine of 2 is, I'm going to have 1/2 sine of -7 minus -1/2 sine of 2.